Work and power, part one. So this next unit deals with looking at how work is defined in the physics sense. And in the physics sense, work is defined as an applied force acting throughout a certain distance, or in physics, displacement. So if we take a look at the unit here, the applied force, the force that you're pushing or pulling the object with in newtons, and the distance it moves, or displacement, in meters. And of course, vector quantity, both are direction dependent. And work, you can see newtons multiplied by meter, we get newton meters, or that's shortened to be joules. The interesting thing here, though, is that work is actually a scalar quantity, as we'll see. But taking a look here, work is done when the applied force and displacement are in the same direction. So the useful work is done when we're looking at the part of the force that is in the same direction as the displacement. Also, work is done when it's in the complete opposite direction, when the force is opposite to that of the displacement. And we'll see how that comes into play later on. So for an example here, let's just say we have determined the work done when a force of 20.0 newtons in the positive direction acts on an object for 8.00 meters, also in the positive direction. Make it nice and easy here. So of course, work is equal to force multiplied by displacement. So our positive 20.0 newtons multiplied by positive 8.00 meters, we get 160.00 newton meters. And if we look at that, of course, we have 3 sig figs in each of those numbers. So 1, 2, 3, that's a 0, so this stays as a 0. The number 160 joules has 2 sig figs, so we have to indicate that that third digit is significant by putting a line over top of it. Or, of course, we could put a decimal after the 0, and that indicates that that 0 is significant as well. So 160 joules. Now, interestingly here, even though the force and the displacement are vector quantities, they're direction dependent, work is actually a scalar quantity. And yet we can have positive and negative work, but they mean something slightly different in this case. If we're doing positive work to an object, that object is actually gaining energy, whereas if it's negative work, that object is losing energy. So that kind of brings another interesting thing into play here, is that work done on an object is equal to the change in energy that happens to that object. And if the object is moving, that we could even simplify that to be kinetic energy, EK, or kinetic energy, moving energy. Pushing a box, the box is moving, that box is gaining moving energy or kinetic energy. So the work-energy relationship here. We have a couple of situations which involve no work. Take a look at those. So some of the obvious ones here. If you have an applied force but no displacement, that's no work. So it makes sense here. You're pushing on a wall till the cows come home, it doesn't move. No work is done because the displacement is 0, which will make everything 0 in that equation there. Kind of vice versa here. No applied force, but we have a displacement. So for example, a cart that's already moving, maybe on a frictionless surface or something like that. We have no force, we have a displacement, and yet no work is done. Work was done in getting it moving, but the scenario in which it's simply moving, that is no work. And kind of an odd case, which we'll come back and look at. If the applied force and the displacement are at right angles to each other, there's actually no work being done in the physics sense. So for example, if you're holding a box up, now in order to get the box to this point, you would have to do work. But holding the box up, in order to hold it, we have to exert a force opposite to gravity, so we're holding it up. And if we're moving forward, which is bizarre, holding a box up and walking forward actually involves no work being done in the physics sense. Weird. We'll see why in the next video as to why that is the case, why there is no work being done.